very happy to talk about this work today. So this work is a joint work with Jocelyn Garnier from École Polytechnique in Paris and with Pierre Millien from Institut Langevin, also in Paris. And it started during the PhD thesis of one of our students, Quentin Gupfer. Okay, so this work focuses on ultrasound imaging. So let me first recall what ultrasound imaging is, or at least the principle. What you have is you have a transducer array here in pink that emits incident waves into the medium. Then the waves propagate throughout the medium and interacts with the medium. And the same transducer array measures the backscattered echoes. And from those measurements, an image is created by applying proper time delays. So if we write this in the time harmonic regime, what we have is we have for frequency omega in our bandwidth B, we have incident spherical waves UI emitted from XE. XE here is a transducer on the array. And so you can express UI as just the outgoing green function of the Helmholtz equation G. With wave number k. Here, k is just omega over c naught, where c naught is the effective speed of sound into the medium. And our measurements are the scattered field US that is recorded on the transducer XR, also on the same array. And with this, the image is computed by backpropagating those measurements US with the green function G. And so this is called Kirchhoff migration. And so you get the following image. So you see that you have a bright spot here that created this reflected wave, and also tiny scatterers in the medium. So over the last decades, you had a lot of technical progress in the sensors manufacturing. And now we have access to extensive computational resources. And so that now the limitations in ultrasound imaging are mainly due to the reconstruction algorithm and the underlying mathematical model of this algorithm. So more specifically, in medical ultrasound imaging, when you consider soft tissues, the echoes that you measure, they don't come from a bright spot just as before. You don't have main reflectors in your medium. What you have is numerous unresolved scatters. So unresolved mean that they are very small compared to the wavelengths. But what they do is they create this speckle pattern that you see on the left on the in vivo image of a human liver. And so state-of-the-art models exist, of course, and what they do is they produce solutions that are stable with respect to the size and the position of the scatterers, but not if you increase their numbers. And here you have tens or hundreds of thousands of them. And so our first goal is to provide a mathematical framework for wave propagation in this random multi-scale media. More specifically, what we want to do is derive a quantitative asymptotic expansion of the scattered field that is measured with respect to the size of the scatterers using stochastic homogenization techniques. The second goal is to then study with this new expression of the measured field, to study the estimators that were introduced by Alexandre Aubry from Institut Langevin and his team of the effective speed of sound in a biological tissue. Our motivations are twofold. The first one is that you see here, I put the Kirchhoff migration functional back, and I highlighted the dependency with respect to the backpropagation speed CS. And so you see that if you choose a CS that does not match C naught, the true speed in the medium, then you're going to have a distorted image. So if you know if you have a good estimation for your C naught, then your image is going to be better. And the second motivation is that the speed of sound is actually a quantitative biomarker that can be used for diagnosis. So our model is the following. What we do is we model the tissue, the domain that we want to image, at the smooth bonded domain D here in pink. And we have an incident wave UI from the array that is in orange. And in D lies a set of small scatterers that are randomly distributed throughout the medium. So they are of size epsilon. That's why I call them S epsilon J. And epsilon is way smaller than the wavelengths, so the inverse of K. And typically, the number of scatterers is of the order of epsilon minus D. So you see that the smaller the scatterers, the more you have scatterer. So that the mean density of scatterers is always constant. The medium parameters in our domain D are given as such. We suppose that the background medium in pink here is homogeneous with parameter AM and AM. And each scatterer is homogeneous, but not necessarily the same as the other scatterers. We have classical assumptions on those parameters, uniform ellipticity, and N is bounded below and above by strictly positive constants. The free space here is also homogeneous with parameter identity and 1. So my talk is going to be divided in two parts. The first part is going to be dedicated to the forward problem. So to obtain an asymptotic expansion of the scattered wave field in the stochastic homogenization regime. And then I'm going to talk about the inverse problem. So first, the forward problem, and we're going to start with the effective model. So if we write what the total wave field verifies, it's the unique solution in H1 log of the following equation. So you see that you have Helmholtz equations outside of D with parameter 1 and 1. Then you have the Helmholtz equation with parameter A epsilon and N epsilon inside D. You have transmission condition on the boundary of D. And of course, the scattered field verifies a radiation condition. The first thing we do is we introduce a ball BR of radius R and the associated DTN operator. So DTN means Dirichlet-Neumann. And with this, we can reduce the equation verified by U epsilon over a bounded domain. So we only consider the equation in BR now. And here we replace the radiation condition by a DTN condition on the boundary of BR. And what we assume is that the sesquilinear form associated to 1 is coercive. So why do we need that? Of course, if we fix just one realization, so one distribution of little scatterer, we know that the problem is well posed, but we don't know that we can control the solution independently of the realization and epsilon. So in order to be able to apply stochastic homogenization techniques, this is the starting point. So we assume that the form is coercive. And so that we can bound U epsilon by a constant independent of epsilon and of the realization. So with this, what we want to do is apply some homogenization techniques. So the starting point is the following. The first thing we do is we write an integral representation of the total field outside the medium. So this is the field that we're going to measure. So outside of D, so for Z in BR minus D, we have the following representation. So the UI incident wave and then two integrals. Here you have the contrast in A, here the contrast in N, U epsilon here, and GK is just, remember that GK is just the green function associated to the Helmholtz equation. So of course you see that you have a U epsilon on both sides. And what we want to do is approximate those terms, gradient of U epsilon and U epsilon on the right-hand side, so just in D, in our multiscale domain, using stochastic homogenization. Okay, so this is what we're going to do now. So first, let me specify what our random assumptions are. So what's random here is the position of the little scatterers. So I call that xj. So xj is the center of each inclusion. And so sj is the inclusion of size 1 centered at xj. And my assumption is that this point process xj is stationary. What does this mean? It means that its distribution law, P, is independent of x. Okay, so no matter where I am, the distribution law of the point process is the same. So with this, I can denote S, the set of inclusions of RD. I can define A and N, similarly as I did before, two parameters that take value AM outside and AJ inside the inclusion J. And so that to get S epsilon, the set of inclusions of size epsilon in D, what I do is I resize those inclusion of size 1, and I take the intersection with D. Okay, so, and then A epsilon, just A of the variable over epsilon, and the same for N epsilon. Okay, so with this process, what do I get? I plotted here two medium for two different epsilon, and what I want to highlight is that when you take epsilon smaller, what you do is you zoom out on this inclusion process of inclusion of size 1. So when you have a smaller epsilon, you have more and more scatters. So a definition that we will need in what follows, it's the definition of stationarity for a stochastic process. In order to define it, I define big omega, the set of all point processes on RD, and I introduce a translation operator on these point processes. So what does it do? It takes a set of inclusion, so a point process, and a point X, and it just translates the set of inclusion by X. And since we assume that the set of inclusion, our inclusion was stationary, then this action is preserved by the measure P, which is the law of distribution of our inclusion. And so for a process to be stationary with respect to tau, it means that if you compute your process at X plus Y for distribution of particles, it's the same thing as computing F with the at X for the translated distribution of particles. Okay, and another assumption that we need, if for this action to be ergodic, I'm not going to specify what ergodic means. It means intuitively that you need your distribution process of scatter to decorrelate at infinity. So if you consider the process at X and at Y, for X far away from Y, those two random variables basically are going to be independent. And a way to understand ergodicity is through Birkhoff ergodic theorem, which tells you that if you take F stationary, then if you average your F over a ball BR of radius R, and you make this ball grows larger and larger, then you get the expected value of F. So it's the same thing as averaging spatially for your stationary process than to average with respect to the realizations. And we're going to use that in what follows. Okay, so with this, with the stationary ergodic A and N, we can apply stochastic homogenization. And so we can prove that almost surely, so for a fixed realization, U epsilon converges weakly in H1 of BR to U naught. U naught is the homogeneous solution, and it satisfies the following. So you have the same equation of size, of course. And inside of D, you have an Helmholtz equation where A star and A star are the effective coefficients. So this means that there are constants that can be computed from our coefficient A and N. You have the transmission condition over the boundary of D and DTN condition over the boundary at the boundary of BR. The homogeneous coefficients quite classically are given as such. If you know periodic homogenization, it's basically the same thing, but instead of averaging over a period, you average with respect to the realization. Sorry. So N star is just the average of N, and A star is computed through the function phi j here, which is called the corrector. And the corrector is the solution to the following equation that is posed in the whole domain RD, so a solution to a Laplace equation with our coefficient A over the whole domain. With the corrector, we can also define the first order corrector U1, which is, as in the periodic homogenization, the sum of the corrector times the derivative of U naught. So with this in mind, what we want to do is construct an approximation of U epsilon and be able to estimate the error that we make. Okay, so in order to establish error estimates, we need a little bit more than just stationary and ergodic. We need a quantitative mixing assumption. So what does it mean? It means that I told you that the scatterer process need to decorrelate at infinity. And actually, what we need is a quantification of this decorrelation. Okay, so I did not write the specific quantitative mixing assumption that we use because it's quite technical, but it implies in particular that the covariance function of the inclusion process is integrable. Okay, so with this, we can prove that the phi j are bonded in dimension 3, and in dimension 2, they grow like the square root of a log. So those are quite recent results from the stochastic homogenization community. So this one is from 2019, and you have lots of work in this area about quantification of the different error in stochastic homogenization. So we can rely on this work from 2019. And so if you do the average of the corrector over a domain of area 1 around x, for each x, you can bound this by either one of the square root of the log, depending on your dimension. And with this, we can prove error estimates for two-scale expansion. So first in L2 and then in H1. So in L2, we can prove that U epsilon minus the homogeneous solution is of order epsilon. And in H1, so we have two terms. We have inside D and outside. Inside D, we have U epsilon minus U naught minus epsilon U1. We need U1 to have strong H1 convergence. And outside D, we don't have U1 because we don't have any corrector, because we don't have any scatterers. And this scales like square root of epsilon. Okay, this was a known result for Dirichlet-Neumann problem, but for Laplace equation, but here it's for Helmholtz equation and it's for the transmission problem. So we needed to introduce the associated boundary characters and quantify them. I just want to give you a bit of idea of the proof. So the first thing you do is you introduce V epsilon, which is just your error, and you write the problem verified by V epsilon. But this V epsilon doesn't verify the transmission condition on the boundary of D. So the first thing you do is you introduce theta epsilon, which is the boundary corrector, which is the function such that V epsilon minus theta epsilon verifies the transmission condition. Okay, and then V epsilon minus theta epsilon is easy to deal with because it's just a transmission problem. And so you deal with V epsilon minus theta epsilon, and the only thing you're left to do is deal with theta epsilon. So here I wrote the equation verifies by theta epsilon. So you see it's exactly the same as U epsilon, but you have oscillatory data on the boundary of D. Okay, so it's a problem of the same nature, but the source is oscillating quickly like x over epsilon. Okay, so it's actually a problem even, I mean, at least as complicated as U epsilon. You have lots of work on those boundary layer correctors in this periodic setting. Notably, they want to understand if you can homogenize this equation or not, and so on. I highlighted this work here because they dealt with the same problem as us, but in the periodic setting. But the tools then are different, but still it was a great help. And also in the stochastic settings, as I said, the Dirichlet-Neumann problem were treated in this work. So then, as I said, you first estimate V epsilon minus theta epsilon, and then you estimate theta epsilon, and you get your estimation of your error. Okay, so can you do better than this effective model outside of D? So what we do is we go back to our integral representation, but we write another integral representation. Before, what we wrote was UI, and here you had the Helmholtz green function. And now what we do is we use the homogeneous green function. So it's G naught that verifies the homogeneous problem. And with this, we can write this integral representation. So for Z outside of D, U epsilon is equal to the homogeneous solution plus those two terms, where you have the contrast, the homogeneous green function, and U epsilon. And of course, what we want to do is replace the gradient of U epsilon and U epsilon by the expansion that we just proved. Okay, so, and this is what we do. We replace U epsilon by U naught and gradient U epsilon by gradient U naught plus gradient U1. And you get a better estimate as before. Before we had epsilon, no, we had epsilon d plus 1 over 2. Oh, no, sorry, we had a square root of epsilon. And so we prove this estimate. And this proof requires, I'm not going to talk about it, it requires to quantify the fluctuations of your two-scale error here. So fluctuations means you need to estimate how this quantity oscillates around its mean. So I'm going to just show you some numerical simulations that we did to validate those first results. So here, I plot the mesh of the domain that we consider. So BR is the ball on which we apply the DTN operator. D is the medium inside which you have the tiny scatterers. Here, you have one realization in this square of A epsilon. And first, we compute our reference solution U epsilon. So here we had a plane wave that originated from the left and is scattered by our medium. Here is the corresponding homogeneous field U naught. And you can do the different U epsilon minus U naught. First thing you notice is that we gain an order of amplitude here. And once you have this, you can also compute this big U1. So you see that qualitatively it's quite close. And you can verify that quantitatively by doing some plots of convergence. So this is what we did. So here, what do we compute? We compute the L2 norm of the error. So first U epsilon minus the homogeneous problem, and then U epsilon minus the homogeneous problem minus this corrector term in L2 of the outside. And then we take the expectation. Okay, so to take the expectation, we need to do some Monte Carlo simulation. So you see that for the zero order approximation, we get a slope of 1. And with the corrector, we get a slope of 2. Okay, so it validates the different convergence rates that we proved. So now we can move on to the inverse problem. Okay, so first, let me recall what the model is. So we consider spherical incident waves UI that are emitted from the array. So not plane waves anymore, but spherical incident waves. So expressed with the green function G, and the velocity in my medium is C naught. So we did two simplifications compared to what was happening in the forward problem. The first simplification is that we consider that A epsilon is 1. So we don't take any contrast in the divergence for the scatterer. So here I plotted just the scattered field, sorry, for an inclusion with contrast in N epsilon and for an inclusion with contrast in A epsilon. And remember that for us, what we measure is just the field above here. So in reflection, you can't really tell them apart besides by comparing the amplitudes. And so it's not that crazy to do this first simplification, is what I mean. The second simplification is we suppose an N epsilon can be written as 1 plus N tilde epsilon, where N tilde is stationary, like before, and the expected value of N tilde is 0. So what does it mean? It means that we match the homogeneous medium and the outer media. So then when we compute the homogeneous problem, it's just the incident field. Okay? And so with this, we can rewrite the problem verified by the scattered field as such. So it's the same as before, but here the contrast is just so k squared, so omega squared over C naught, and 1 plus N tilde, where the expectation of N tilde is 0. So that what we want is estimate C naught, which is the effective speed of sound in our medium, from the measurement of US. So for each incident wave emitted at XE, for each measured field at XR and for all frequency omega in our bandwidth. Okay, so regarding the state of the art, so in the mathematical community, you had quite some works that have been developed in the recent year to apply the full waveform inversion to ultrasound measurements. So initially, the full waveform inversion is widely used in seismic applications, but recently it was used to image with ultrasound measurements. So the idea in the full waveform inversion is with a guess of a speed of sound map to compute the scattered field that is associated to this speed of sound map and to compare it with the data. So it's quite heavy in numerical simulations. So our approach is very different, and it comes from the physics side and from a method that are called focusing method. The idea is that is quite the same as when you have a photo camera and you do the focus on your camera. You define a focus criterion and you try to maximize this focus criterion by tweaking your speed of sound. And when you have the good speed of sound, then the focusing criterion is going to be the greater. And so especially we worked on the estimators that were designed by Alexandre Bruyère and his team. So first, I'm going to talk about the point spread function of our imaging setting, and how the point spread function is affected by a wrong backpropagation speed. So the point spread function, first definition, is the response of an imaging system to a point-like reflector. So for this, I consider my setting here, but with only one reflector. So I have my array in orange that emits the spherical incident wave. I have just one reflector of size epsilon that is quite small compared to the wavelengths, and I measure the scattered field. So here NTL is just NS. NS is the contrast of the reflector, plus the indicator of my reflector. Here I just took a ball, that is located at X0 with radius epsilon. Okay, and in order to have explicit formula, we consider the partial asymptotic regime. So in this regime, we're far away from the array. So the wavelength is order eta, the transverse lengths are of order square root of eta, and the axial lengths in my medium are of order 1. And of course, epsilon is still quite small in front of eta. Okay, so I have numerous scatter per wavelengths. And so first, let us do some numerical simulations. So I recall here the imaging function. So if you want to compute your image at point xs in your medium with backpropagation speed cs, you do as such. So you backpropagate your data, so your measurement of the scattered field, with the green function with speed cs. Okay, so here I plotted the PSF, so just the imaging function, for different CS. Okay, so some notations here. Nu is the ratio between C0, the true speed, and CS, the backpropagation speed. Okay, so on top here, you have the PSF for the true speed. Okay, so you retrieve exactly what you expect, which is a bright spot that is that has the proper dimension as the state-of-the-art literature. So you know that the longitudinal resolution is given by B over C0, and you know that the axial resolution is given by, so A0 is the size of the array, omega 0 is the central frequency, C0 is the speed, and Z0 is the depth of the reflector. Okay, then what happens if you don't take the good backpropagation speed? So on the left, you have a faster backpropagation speed, and on the right, slower. So you have three effects. The most obvious is the shape. The shape of your PSF is not the same. The second effect is the position. If you look on the left, you can see that if you choose a faster backpropagation speed, then your bright spot is higher in your image, which makes sense, of course. And the third effect is the amplitude. You see that here on the right, where you have the scale, you have a factor 10 in the amplitude between the wrong backpropagation speed and the good backpropagation speed. So what does it tell you? It tells you that if you take the amplitude of the imaging function at your bright spot, then that's a good indicator for getting an estimator of your speed of sound. And this is exactly what we're going to do. So first, what we do is we write explicitly what this imaging function looks like. Okay, so by doing this, we are able to determine the position of the bright spot on your image. So this is this XF. Okay, so we have the position of the bright spot. So it depends on the position of the reflector, X naught, so Y naught and Z naught. And it depends, of course, on the ratio of your velocity. Okay, and with this, we compute the imaging function at a point near this bright spot. So we have the point where the bright spot here is plus a tiny error, and we are able to compute the imaging function here. And so we get that it's proportional to P1, where P1 is what I call here the narrowband PSF. So here I wrote everything in 2D, but you have the same thing in 3D. And so you have you retrieve your three different effects. So first you have the position of your target that is not the same when you have a bad backpropagation speed or false one. Then the shape is different. So here you have the shape. So here Z2 is your error in the longitudinal coordinate, and you retrieve the good resolution here. So you have the peak function around Z equals 0. And here, the same thing for the transverse coordinate, okay? With here, the resolution with the transverse coordinate. So this gives you the shape of your PSF. And here you have the amplitude. G here is the peak function that I wrote here. I'm going to plot it in the next slide. And this last term here is a term that interests us. Because so what does it tell you? It tells you that you have a peak where nu equals 1. So remember that nu is the ratio between C0 and C0, so between CS and C0, so that's a good thing. And moreover, you know that you have a peak, but you have the width of the peak. So you have the resolution of your imaging system with respect to the speed of sound. Okay, and this resolution is given by this, so it depends on C0, Z0, the depth of your locator, A0 squared, A0 is the size of the array, and omega naught, the frequency, the central frequency of your bandwidth. Okay, so here you notice that if you take Z1 and Z2 to be 0, so if you compute the imaging function at the bright spot, like we said, so this is what we do here, everything cancel, everything 0, but this third term here, and it gives you the peak around the good, the proper speed of sound. Okay, and this is what you get here. So if you take the max of this imaging function at the bright spot, you get so nu here is the ratio between the two speeds. So you with respect to different backpropagation speed, you get different different amplitude for your imaging function at the bright spot, and it gives you this curve. Okay, so in red it's the theoretical one, so it's this function g, and in blue it's a simulation like in the previous slide. You can actually do a bit better. If you plot the imaginary part of I, you can see that you have a jump of your imaginary part when the backpropagation speed matches the true speed. And this peak is narrower than this peak. Okay, so this is what I plotted here. If I plot the derivative with respect to the backpropagation speed of the imaginary part of I get this indicator, this estimator here, which is a bit better than the previous one. Okay, so now let's go back to our random multiscale medium. So as I said in the introduction, in soft tissues, the echoes don't come from big, bright scatterer, they come from numerous unresolved scatterer. And so the difficulty is that we don't have any target to focus on, just as before. So how do we do to recover the effective speed of sound with the same principle? So the idea of Alexandre Aubry's work is the following. What he does, and with his team, he recreates a virtual guide star. So before reflector was, if you want, a guide star that you could focus on to retrieve your speed of sound. So here he recreates a virtual guide star by repeatedly focusing in a small area of interest. So the guide star is going to be the equivalent of our bright spot on the image, and why repeatedly is to get rid of the randomness. So first, let us recall what the scattered field verifies. So the scattered field verifies the following equation. Remember that n tilde is stationary, it's mixing, its expectation is 0. Okay, so mixing as before, it's some decorrelation properties. So here, what we need is for the covariance function of n tilde to be integrable. And with this, we can, with stochastic homogenization method, get an approximation of the scattered field just as before. So before we had two terms, here we just have one term because we don't have any contrast in A. So we have k squared integral over n of the contrast times the two green function. Okay, and here the estimate is a little bit better as before, because actually we don't need all the heavy tools that we had before with contrast in A, and you get a tiny better estimate as when you have some A's. So now we can express the imaging function at a point xs in our domain. So we take xs in D and we compute the imaging function at xs for a backpropagating speed cs. Okay, and you can approximate it by this. So what you get is a convolution between the random contrast and a PSF over a small area. Okay, so you get a small, only a small area around the point xf contributes to your image at xs. Okay, and so xf, if you want, is the equivalent of it's the point you are probing in your media. And so you see that whenever I change my velocity cs, this xf here is going to move as in the little animation here. So what I do is as before what we did for the bright reflector is evaluate my imaging function at the bright spot. So here I do the same thing. I choose an xf so that it is constant whichever speed cs I am considering. And what's moving is my xs. So no matter which xs I take when it has this form, so x, xc, t, xc is in R, t is positive, I choose my point xs like this so that I'm always focusing in the medium at the same point. So if you want, x star is the same thing as my x naught before, and I'm probing my function I at this xtt, so that I'm always looking around the same x star. And so with this, what I notice is that my integral is is a convolution between this n tilde that oscillates quickly, because n tilde epsilon is the contrast of the tiny scatterer. So if you look a bit aside for your point, this n tilde epsilon is going to be completely different because it oscillates at the scale of the scatterers, whereas my PSF P2 is going to be pretty much the same because it's a slowly varying thing. And so with this in mind, what I can prove is that my function here, my imaging function here is asymptotically stationary. Okay, if I compute my imaging function at a point xct, and I compute the imaging function at xct plus eta times a delta x, it's as if I'm computing my imaging function for another realization of scatter. Okay, and so with this in mind, I can use this to get rid of the random effects in my imaging function. Okay, but now that I know that I'm stationary, what I do is I choose xct, and I average locally the square of my imaging function around this xct. And remember that average locally, especially, is the same thing as averaging with respect to the realization if I have a stationary ergodic process. So by doing this, what I get actually is just the expectation of the square of my imaging function. Okay, and with this, I have something deterministic that I'm going to be able to use to build my estimator. So let us show some numerical simulation. So this is a type of medium that we use. So we did this with K-wave. So here Z is the depth of your medium. And if you zoom in, you have all the tiny scatter. Here, lambda at the bottom is the wavelength. So you see that you have a lot of scatter per wavelengths. And so what you do is you choose a point to compute your imaging function, and you average locally this the square of your imaging function over an area of size of order lambda. Okay, so here I plotted the module of I for different points. So on the here on the Y, you have all the different points around my XS, and on the bottom, on the X, it's the different speed of sound. Okay, so you see that for nu equal 1, so for the true speed of sound, it's basically yellow. So you're going to be able to retrieve this information if you do an average with respect to the realization. And this is exactly what you get. So the first estimator, so here in red, you have the theoretical one. In blue, you have the simulation one, the simulated one, and you see that they quite agree. And for nu equal 1, you get a good estimator by getting the maximum of this average I. Okay, and so here, if you look at this matrix, you see that here we retrieve, if you want, the first estimator that we had for the reflector, in the sense that we took the max of the imaging function. Remember that we had a better estimator by taking the derivative of the imaginary part. But with this, we lost everything on the imaginary part because we took the module. Okay, so if we want a better estimator, we have to do something a bit more subtle. So what you do is you look at this matrix and you see that if it would be separable with respect to the realization and nu, then you could get the information about your imaginary part. And this is almost true. What you can prove is that if you consider the kernel operator defined as follow, and you compute k times k star, where k star is the adjoint of k, then what you get is this operator S, and you can prove that this operator S is basically, it's at first order deterministic. Okay, you get that it's the integral over the interval of speed that you're probing of P2. Remember that P2 is a PSF times P2 bar. Okay, but probed for C and for CS. And so by taking the first eigenvector of S, which is the first singular vector of K, you're going to be able to recover the speed of sound. So here is a plot of S. You see that, so S is just K times K star, where K is the matrix that I just showed you. You see that when you do K times K star, you get something completely deterministic. Here is the imaginary part of S. And then indeed, if you take the first singular vector of K, so the first eigenvector of S, you can take the Argmax of U, you get this estimator here, and you can take the derivative of the imaginary part of U, and you get a better estimator. Okay, and last, I want just to compare what we had with the experiments that Alexandre Brie student has done in his thesis. So this is the experiment setup. He probes a phantom here and compute the different estimator here. And compared to what we have, this is it. So in blue, what you have is the first estimator when you average the square root the square of I. In red, this is the estimator when you take the Argmax of the first singular vector of this matrix K. And in purple, it's the derivative of the imaginary part. So you see that qualitatively, we get very similar results. So we were very happy about that. Okay, so to conclude, what we did is we first developed a new model for wave propagation in random multiscale media using quantitative stochastic homogenization techniques. Then we used this model to study the estimators of the propagation speed introduced by Alexandre Brie and his team, but in the context of ultrasound imaging. We have lots of perspectives for this work. The first thing we are working on is to extend this to more realistic situations where you don't have a constant background speed for your medium D, but you have a slowly varying speed for your medium D. So your medium D, your medium would be a slowly varying speed plus the tiny scatters. So when you take the homogenized model, it would be a slowly varying homogenized speed. Then we want to extend this method to inhomogeneous media, where you have contrast both in the bulk modulus and in the density. And finally, you could extend also the homogenization results to other waves equations as Maxwell or elasticity, if you want to consider different applications. So thank you for your attention.
Great, thank you so much, Laure, for an excellent talk. So that was very nice. Any questions for Laure? The floor is open for questions. So I was wondering, Laure, so you have sort of this special type, or the medium is sort of with inclusions. Would it be impossible to look at continuously varying media also? Would that be with your framework?
Oh yeah, it doesn't change anything as long as you can write it as n of something over epsilon and s is stationary. The result is the same. Actually, it's just for the applications that we wrote the model as such, but mathematically, it's you obtain the same results.
Right. Great. But it's important that it is sort of mixing. So what if you have long range? You don't have integrable covariance.
So
what
actually the process that we consider for our inclusion, it doesn't have long range, but it has some correlations. Because we take the inclusion to be at a minimal distance from one another, and so you get this hardcore Poisson point process, which is a bit more complicated. I mean, at least it's not finite range dependence. It's more complicated than that, but we didn't look at long range correlations because like physically, this is like I showed at the end. This is what they do, just to probe a bit aside the focusing point. And since this is working, we suppose that we have like not so much correlation, but in other contexts, it would be interesting, maybe, I don't know, in metals, or I don't know, to look at different type of correlations for sure.
Any other questions? So I have one more question. So what was the role again? Now you have the number of scatters and epsilons was sort of scaling with a parameter d or something. You can choose a general d, or do you have a certain sort of relation for the number density of scatters?
I mean, what we need is for the size of the scatterers to be one order less than the wavelengths, or
Wavelength,
two order,
yeah.
I mean, way smaller.
Yeah.
But we actually don't know, like, in the application, how much smaller it is. Maybe hundreds or dozens, or. But what's important is for you to have quite a lot of scatter pair wavelengths to be in a realistic situation. And actually, this makes the simulation quite challenging, because you have maybe 80 wavelengths in your medium, and you have dozens of scatter pair wavelengths. And so if you don't use efficient numerical methods to have numerical simulations, it's quite challenging. So we're actually also working on that.
Yeah. Well, thanks so much again, Laure. So
Thank you for the invitation.
sure.